This is part 2 of lesson 10.4, comparison of series. In this short part of the video, we're going to talk about the limit comparison test. So now we're going to suppose that we have two series, one a sub n from n equals 1 to infinity, and the other is b sub n from 1 to infinity. And both series, and this is important for all these terms, these tests so far, is that they have to have positive terms. So now what we're looking at is if we take the limit of the ratio of these two series, that we want them to equal a real number L. So it's important that that is a real number. If that's the case, then we can say that both series either converge, both series either converge or both series diverge. So this is the idea again, because you're comparing the two series, that you choose one that you know either converges or diverges. Then if you do the limit comparison test, they both have the same behavior. So as it states here, this test is a great tool for comparing messy algebraic series, such as the one given in the example here. That can be kind of messy. And we can compare it to something pretty simple that we know converges, like 1 over n squared. That's a simple p series that does converge. And a big note here, and we kind of did this earlier in the lesson, you need only consider the highest powers of n in the numerator and denominator to do this test, to have it work out the way you need it to. Okay, so for example 2, we're to apply the limit comparison test for each of the series below. So in letter A, what I want to let it compare it to is I'm going to let my b sub n be 1 over n to the third, which I know is a convergent p series. So then I'm going to use the limit comparison test I'm going to take the limit as n approaches infinity of the term that I'm trying to determine its convergence of, divided by the one I know about. I'm going to simplify this, find the limit, and then I can make my conclusion. Hopefully I get a real number, because since I know that p series converges, my new series is going to converge. So when I do this, what I get is the limit as n approaches infinity. And the nice thing about a lot of these is you can use your horizontal asymptotes tests to determine this. So you can see that that's going to equal 2, and you want to note here that 2 is definitely greater than 0 but less than infinity. So you can say, since, and you can be kind of general here, the series b sub n converges, then you can say your a sub n also converges. And if you notice, we've already said what test we were using, the limit comparison test, so you don't have to list it again in your conclusion. And then finally, letter B, we have, that's kind of a messy rational function. So what we want to do again is pick a b sub n, and what we're going to notice here is if we look at the powers, and we think of this as n to the fourth over n to the fifth, we end up with 1 over n. And of course, that is the harmonic series which diverges. So if we do get a real number, what we're going to say then is that both of these series diverge. So using the limit comparison test, going to take the limit as n approaches infinity of our unknown series, nth term, and we're going to divide that by our harmonic series. We're going to simplify that. So we are going to get the limit as n approaches infinity of n to the fifth plus 5n over 4n to the fifth minus 2n to the third plus 3. So this is going to equal 1/4. And of course 1/4 is greater than 0 but less than infinity. So since our b sub n diverges, our given series diverges. Okay, I know this was a short video, but I didn't want to make part 1 too long. So now we have our limit comparison test. And this is actually a test that we use quite a bit for series, so it's going to become very useful going forward. So if you have any questions, you can contact me, and I will help you as best as I can.